listeners, to another episode of the Dark Assassins podcast, the show that dives deep into not just technology, but the concepts, software, and procedures behind it all, and explains it so simply that even your grandma can understand it. As always, I'm your host, the Dark Assassin. We've talked quite a bit the past few weeks about Swift, the programming language, with the whole implementation of my elite encryption algorithm that I've been working on in it. And now that I've finished that implementation, I guess spoiler alert on that one, I wanted to talk about the language and kind of give a little bit of a review, if you will, and also try to remove the stigma that I, and I'm sure a lot of people have out there, that Swift is just for Apple devices or just for writing programs made to run on Apple devices, because there's definitely a lot more to it than that. So that's coming up on this week's episode. But before we get into that, let's start off with our trivia question for the week. So an operating system kernel runs at what protection ring on a CPU? So what is the protection ring on a CPU that the operating system kernel runs in? And that is your trivia question for the week. Now, before we get into this week's cybersecurity tip, I wanted to have us put on our tinfoil hats for a second, because I have a conspiracy theory for you that I completely made up in all good fun, and by no means necessarily think this is true, but I just happened to come up with it because I like to do things like this sometimes. So we all know about the whole CrowdStrike fiasco that happened last week. And my tinfoil hat conspiracy that I have absolutely no evidence for whatsoever, aside from making a semi-logical argument that probably has a bunch of holes in it if you actually tried to fill it with water. But what if this whole CrowdStrike fiasco was just to garner more market share? And again, this is one of just those wild conspiracies that I come up with just for fun. But here is the basic premise of it, right? So your average Joe, and I'm assuming the vast majority of people before this whole CrowdStrike fiasco happened, had never heard of CrowdStrike before last week. And now it's practically a household name. So what if this was just a whole PR stunt in order to garner, more attention to it in order to gain more market share? Because after all, there's a saying out there, right, that all news is good news or something like that, or like all press is good press, basically free publicity, if you will, regardless of if it's positive or negative. Just getting your name out there as kind of like free advertising. And boy, have they gotten a lot of free advertising, because so many people have been talking about this. With, of course, when you have all of those various devices around the world that basically halt the entire globe in some cases, kind of gets to be a big deal, and a lot of people are talking about it. So perhaps, with more people realizing what this company is, perhaps maybe they're looking into them and potentially thinking of buying their service. Although I guess on the other hand, it could go the opposite way too, that they see this massive issue with this company and now they're going to be like, I'm going to steer clear of them forever. So maybe there's two sides of it. Maybe this is all just a big old nothing burger. It probably is, because like I said, this is something I just completely made up for fun. So I'd be interested to hear what you think of this, though. I mean, how many holes that there are in this argument? I'm sure there's a ton of them, because like I said, just made it up. But I think we can take our tinfoil hats off now and move into this week's cybersecurity tip. Now, for this week's cybersecurity tip, I wanted to kind of talk about more of a broader range of topics, if you will, and that is about this idea of avoiding social engineering attacks. And one of any attacker's most powerful weapons at their disposal isn't their exploits or even their malware tools that they have. It's often their social engineering skills, and social engineering attacks is really what gets a lot of people. And if you're wondering what social engineering is, let's kind of go over that real quickly. So essentially, social engineering is a way of getting someone to reveal enough information about themselves that they end up compromising themselves. So an example of this is I saw like a video a while back. I don't remember who posted it or anything like that. I just remember seeing this video where essentially this guy was going around asking people what their passwords were. And of course, the smart people aren't actually going to tell him what their password is, but they might give like some inclinations about what comprises their password. So anyway, this one person that he goes up to, he asks them, hey, what's your password? And they're like, so my password is, my dog's name followed by the year I graduated college, or something to that effect. And granted, that's not a particularly good password, but I mean, depending on how you used it, you could potentially have some uppercase and lowercase letters and some numbers. So as far as password complexity goes, it's definitely not the worst one in the world, but it's also not great either. But anyway, it gets even worse because here's where the social engineering aspect comes in, right? So the first question was, what's your password? Of course, they don't say the password, but they give what the password's comprised of. And then because they mentioned to him that the password involves their dog's name followed by the year they graduated, he then proceeds to have a conversation with them and asking them questions like, oh, what kind of dog do you have? Oh, cool. What's your dog's name? And of course, that's where they spill the beans on what their dog's name is. And then he's like, oh yeah, and you mentioned you graduated from college. What college did you go to? They say the college. And he's like, oh, and what year did you graduate? And they give the year. And then just like that, they essentially compromised themselves and gave him their password without actually giving him their password. So this is kind of one example of a social engineering attack. But the more common one that I'd say that most people would become familiar with and encounter is phishing attacks. And phishing attacks are one of the most common types of social engineering attacks. And the most common ones are, someone trying to act like someone they're not to get you to reveal information about yourself, whether that's credentials to your bank account or your Amazon account or whatever account it is, in order to log into your account pretending to be you and do whatever they want. So one of the ways that you can help protect yourself from this is to do things like verify the links you click on, verify the sender, because oftentimes what happens here is the person posing as someone else, there's a couple big giveaways. The first one is the email address that the sender is sending you the email from, because more often than not, it's not actually from, whatever company they are claiming to be from. So that's giveaway number one, is you definitely want to check who the sender of the email is. Number two is the way that they tend to get you is by sending you a link to a malicious site that appears to look at whatever site they're, trying to get you to log into, because in case you didn't know, there are tools out there that will auto-generate these sites for you. So really all you need to do is provide a domain name and hosting. So it's fairly trivial to set one of these, scam sites up. And the common tactic is to have a portion of the URL look like the actual website, but then add some other miscellaneous things into the URLs as to not, stomp on the actual original domain. So for instance, if the original domain was like Capital One, they would try to do other things to get around it, like maybe replace the A with a 4 or the O with a 0, or add like, if Capital One, I'm actually not 100% sure if this is Capital One's URL, but if it's like CapitalOne.com, they might do something like CapitalOneBank.com or Bank bank@capitalone.com or something like that, playing around the name to try to make it look semi-legitimate without actually being the legitimate name. So that's another thing that you can look for. And if all else fails, what I would do and what I personally do is whenever I get one of these emails or text messages or whatever that kind of sort of potentially seems legit that I'm not 100% sure about, the foolproof plan to ensure that you don't fall for one of these scams is to go to the vendor directly. So for instance, if someone is emailing you about suspicious activity on your credit card and asking you to log into your portal at this URL, don't use that URL. Go directly to whoever your credit card company is. Go directly to that site, log in, and check there. Because if there actually is something up, there should be something somewhere on your dashboard. And if there isn't something there and you really want to find out, you could, somewhere on that page, there should be a phone number for you to call for the credit card company that you can get on the phone with someone and ask them directly, is this legitimate or not? Because it's definitely something that you don't want to fall for, because if, for instance, if it's like a bank account or a the mortgage company or something like that involving financials, that can really mess you up. And the other thing too is if they're asking for, other kinds of personal information like social security numbers or credit card numbers or things like that, in addition to accounts, if they get information like your social security number, for instance, or like a driver's license number, that could be something that they could use to then steal your identity and open up other accounts in your name, and it can be a whole mess. So to summarize here, whenever you get any sort of correspondence from anyone, virtually anyway, you want to make sure a couple things. If someone texted you or called you, you want to verify the phone number that called you. If someone emailed you, you want to verify the email address of the person sending the email. Is this email legitimate? Check the URL they're trying to send you to. Is this a legitimate URL? Is this actually the URL of wherever? And if you're still unsure about any of those, go directly to the site in question and contact the site directly, whether that's logging into your account directly through that website, or calling the number that's listed on the actual website. And don't click any of the links provided in the correspondence. Or if they're or if it's a phone call, for instance, and they're, saying to call them back at this number. For instance, if it's your mortgage company, for instance, saying that there's an issue with your mortgage and you need to call them at this number, don't call the number they gave you. Go directly to your mortgage company's website and then find the number there and then call them to get the confirmation that way. And that will basically help prevent, you from falling for some of these phishing attacks, because especially with the rise of AI, they're definitely getting a lot harder to spot, at least from the text portion of it. So kind of one of the big giveaways before was the emails were sometimes poorly worded. But now that you can just, generate a phishing attack email from using AI, it definitely is getting harder and harder to detect. But, the links and the emails that they're coming from and the phone numbers and whatnot, those can be some giveaways. But again, at the end of the day, if you're not sure, go directly to the source and don't click any of the links or call any of the numbers that they give you. And that is your cybersecurity tip for the week. So at the beginning of the episode, I kind of spoiled this next portion already. But anyway, let's get into what nerdy stuff have I been up to this week. So as I alluded to and spoiled at the beginning of the podcast, I finished up, I guess finish could be in air quotes, because at the end of the day, is any piece of software truly finished? You can make that argument if you want to, but for the sake of working on it continuously. I say it's basically done at this point, or finished. So when we left off last time, there was just like a few touch-up things that I wanted to do, and I kind of got those done this week. So the first one being multi-threading. But I kind of have to put that in quotes because Swift doesn't really have multi-threading. Like, it does, but it doesn't. And so, unlike other programming languages like C, Java, or even Python, you don't spin up threads in Swift. You what you do if you want to do something concurrently is you create a function and label it as asynchronous, and that will basically allow the function or allow multiple functions to run at the same time, so you can essentially run multiple jobs at once. But from the programmer's perspective, there is no creating and joining of threads like you would typically do in other languages. So that was rather interesting, but you can essentially simulate spinning up multiple threads, if you will, by essentially successively calling the async functions over and over again to essentially run multiple jobs at once. But again, there's no like actually creating and joining of threads, and all that's essentially done behind the scenes. The only kind of caveat to the async functions, which can be kind of a trap, is async functions are like the GPL license, where it's a viral thing. And what I mean by that is if you create a function way nested down in the runtime of your program, it essentially it kind of forces every function that calls it to also be asynchronous. Now, there are ways you can get around this depending on what you're trying to do, but generally speaking, you kind of have to make every single function that calls an asynchronous function asynchronous. So if you don't plan it out ahead of time, you can essentially be tracing back a ton of functions that need to be called asynchronously or transition to be asynchronously, because if one function is asynchronous and two other functions call that function, and those two functions are called by 10 other functions, well, you can see how this kind of grows exponentially and becomes quite viral. Now, like I said, there are some kind of ways that you can get around this depending on what you're trying to do, but yeah, it's just something that you kind of have to be mindful of. And then the other thing I did was I got a config file working. Now, there's really not much the config file does, but I made it so you can essentially specify where you want the program to search for your keys from, which personally I think is a huge quality of life improvement, because before it was basically whatever directory you run the program from is where it's going to search for your keys. So if you wanted to store like all your keys in one central location, or you wanted to not have the keys in the folder you're looking for, you can essentially configure that. But that was the Swift version, but we're not done talking about the encryption algorithm implementations, because I started updating the C implementation to bring it back into feature parity with the Swift version. Because which is kind of funny, because I was modeling the Swift version after the C version, but then I implemented additional features in the Swift version that weren't in the C version, so now I'm essentially updating the C version to bring it in line with the Swift version. But as of right now, functionally, the C version is, I will say, quote, in line with an asterisk with the Swift version as far as functionality goes. The only thing the C version doesn't have now that the Swift version has is the ability to just encrypt and decrypt text without having to do it via a file or a directory. So the big difference functionality-wise between the Swift version and the C version was the Swift version would encode everything that it encrypts in base 64. And then, of course, when you're trying to decrypt, you have to decode it from base 64 before you can decrypt the data. But the C version didn't do any of that. So if you would encrypt something with the Swift version and then tried to decrypt it with the C version, it wouldn't work. But the Swift version was backwards compatible, so if you gave it data that was encrypted but not encoded in base 64, it would be able to handle that situation and still be able to decrypt the data, which is a pretty trivial workaround. Really, all you have to do is essentially try to decode the data from base 64, and if it doesn't work, you can assume that the data wasn't encoded in base 64, and then you can just go about trying to decrypt it normally. So basically got that kind of transitioned over to the C version. So got the functions to do encoding and decoding of base 64, and then updated the encrypt and decrypt functions to actually implement that. So it'll basically try to encode and decode, and if it fails, it'll just kind of resort back to not using that, which essentially makes it fully backwards compatible with the original C implementation that didn't base 64 encode everything. So that was definitely a huge update, I think. The next thing I do kind of want to work on, which I haven't gotten to as of this recording, is to get config files working, because I think, like I said, with the Swift version, that's kind of a pretty big quality of life improvement. And then I guess as far as getting text to be encrypted and decrypted, like having that as an option, not sure if I'm gonna get that implemented. I mean, I probably will, just to bring them into full feature parity. But as it stands right now, I mean, worst case, all you do is if you have text you want to decrypt, you could just create a text file, throw it in there, label it .eea, and then decrypt the file that way. So not technically as convenient, but I mean, there's still that workaround at the moment. But yeah, the big update was, getting the base 64 support into the C implementation to make both the C version and the Swift version compatible. And I did some basic testing just to make sure it works, like created a set of keys with the Swift version and encrypted a file, and then copied and then used that same keys file and encrypted file with the C version and was able to decrypt it successfully, and vice versa. So definitely cool to see them working interoperably. I can't say that word, but interoperability, having that interoperability between the two, and having, if you use one, it works in the other. And then of course there's the Java version, which is still behind as far as feature parity goes, and it's kind of always been the odd one out, because, well, I guess I shouldn't really say that, because at the very beginning, when I made the C version, you were able to decrypt and encrypt between both of them, no problem. The only issue was the keys, because how the Java version currently saves keys is completely different than how the C and Swift version save keys, because the Java version, if I'm remembering correctly, uses the serializable feature in Java to essentially save the keys, whereas the Swift and C version first encrypt the keys and then currently write them to base 60, or encode it to base 64, and then write that result to a file. But before, the C version would just encrypt it and write that data to a file. So technically the keys don't work, or at least the keys files, I'll say, don't work between the C and Swift versions and the Java version. So if you tried to use keys made from the Java version in C or Swift, it wouldn't work. And if you tried to use keys made from the C or Swift version in the Java version, it wouldn't work because how they're saved. But if you actually had the keys themselves, you could manually enter them in either version, and you would be able to decrypt just fine. Although now with the base64 implementation of all encrypted data being encoded in base64, that kind of leaves the Java version out of the loop. But if you encrypted something with the Java version, because the Swift and C versions are backwards compatible with non-base64 encoded data, you would still be able to decrypt that, assuming you manually entered the keys. But like I said, I'll probably go back to the Java version and update that to try to make it more interoperable with the C and the Swift versions. So yeah, that was the updates to that. And I guess with the remaining time we have, I kind of wanted to give my verdict on Swift, I guess, because I talked a few weeks ago when I was first kind of getting into all this on how much I was enjoying Swift, and kind of, posed that question of, will Swift overtake C as my new favorite programming language? So I guess first things first, this implementation of my encryption algorithm was really the first big project that I used Swift for. Now, yes, in the past, I've written a few different iOS apps, but in regards to how much of the language I actually used, those iOS apps were fairly limited in scope, mostly dealing with the Swift UI elements and not necessarily a ton of back-end code to actually handle things like processing data and that kind of stuff. Because sure, there was some basic networking going on and some working with core data in some of those apps, but the specific use case of the apps, or rather, there were also implementations where I would just make apps specifically to show off implementing a certain feature. Like, for instance, I talked maybe last year, or maybe I don't remember when it was, basically creating an app specifically just for implementing and showing how to implement like Face ID and Touch ID. So there's been instances like that, but the majority of it has been fairly basic and not much touching of actual code, and mainly just like Swift UI basic stuff and updating text and that kind of a thing. So not necessarily a ton of like actual Swift programming, if you will. Like, it's like writing a website, but all you're doing is writing paragraph tags, right, within the HTML. Like, yeah, I guess you're technically writing HTML, but also you're kind of just writing text on the screen. But anyway, so that was really kind of the extent of my experience previously. But this was kind of the first project that actually required what I would consider a real use and real implementation of things like algorithms, implementing logic in the code, and requiring the use of more components within the language itself. So I guess first we should get into the things that I like about Swift, and then we can kind of get into the things that I don't like so much, and then kind of give the final verdict. So starting off with what I like. Error handling and propagation within Swift is super easy and just super convenient to do. So kind of like other higher level languages like Python, and even Java has it, and to a lesser extent C++, they have the ability, Swift has the ability to, do things like try catch statements, or in Swift land, it's like do catch statements with tries within the do. But regardless, it's really easy to, have functions throw errors and create specific errors for your function. So rather than just, relying on the pre-canned errors, you can create your own custom ones, add custom text to those errors when they trigger or get thrown. And then you can easily propagate those errors back up the stack, back to whatever function you needed to actually resolve and handle that error. And it's just really, really easy to do. And you don't have to worry about checking for null cases necessarily with all that, and you can just throw errors and handle them accordingly. Really nice. The other thing I like is it's really fast, and it's a compiled language just like C and C++ is, and I guess Rust and Go and like those compiled languages. So it's really nice, and that's because that's one of the things that I really enjoy about coding in C and C++ is how quickly they execute, how fast the executables are, because the code that you write gets compiled directly down to the machine code that your processor understands, so you don't have to worry about some kind of interpreter running to translate the code like Python does, for instance, or you're not worrying about having like an intermediate language like Java does, where it technically is compiled, but it compiles down to the Java bytecode, which is then interpreted by the Java virtual machine, which then runs on the CPU. So definitely, of course, Java is faster than a language like Python, but compared to a language like C or C++ or even Swift, it's not nearly as fast. So having Swift essentially compile the code right down to the machine level and run super fast and be comparable to C and C++ is definitely very nice. The other thing that I like is you don't have to worry about memory management, but I also have this listed as a con in the what I don't like section, so we'll kind of get to both angles of it. But in regards to why I like not having to do memory management, one thing that I personally really enjoy about C and C++ is the level of control it gives you in regards to controlling your memory. The only issue is if you're doing a lot of memory manipulation type stuff, like anything with strings or resizing of data structures or arrays, the verboseness that you have to implement the verboseness of your code, especially in C, when it comes to managing memory, can be quite terrible. Especially if you're trying to ensure that you account for all edge cases. Like if you don't care about all the edge cases and you're not necessarily worrying about your code going into production, yeah, sure, you don't necessarily need to always check the return value from every malloc or realloc call to make sure you didn't get null back, right? But if you really want to ensure that your program is robust and not gonna be susceptible to edge cases like that, you really have to check null cases. And it's kind of going back to one thing I liked about Swift, the whole error propagation thing. Error propagation doesn't exist in C. So you basically are passing null values back up the stack or return number values back up the stack and then handling them that way. But of course, because you have to manage all your own memory, if you get down to a certain point in your function and you've already allocated, a couple chunks of memory, then you have to go and free everything, and you have to be conscious of, I get to this edge case where I got a null back, how do I handle that? Am I going to return something? If I do, what does that mean for other memory I allocated? There's a whole lot of extra stuff you have to worry about with C, which on the one hand is really nice because you can ensure that you know what's happening with your memory, you have control of it, you can specify exactly how much you want. But on the other hand, it gets kind of old after a while if you're always checking for null values and having to ensure you're freeing everything, and it can be kind of a pain. But with Swift, everything is much more concise and can easily be handled with exceptions and throwing errors and handling those errors, which honestly was kind of a breath of fresh air, because going back to updating the C implementation of the encryption algorithm, so many null checks. Because now granted, you don't have to do them, but of course, since I want to make this software as robust as possible, you kind of have to do it. But kind of doing the Swift implementation, not having to worry about all that, was definitely kind of nice. So the next thing I wanted to talk about was the distinction between let and var. So Swift makes it really easy to specify essentially the scope of variables, or the mutability or immutability of variables. So essentially, if you declare a variable with the let keyword, that's basically guaranteeing that that variable will not be changed, which is very nice. And then kind of on the other hand, if you use var, it basically explicitly says that this variable can be changed. And the other thing that's kind of nice about the variables is you can be as verbose with them as you want to. And what I mean by that is you can use variables like you would with a language like Python, for instance, or you can explicitly type the variable like you would with something like Java or C, for instance. And what I mean by that is you can do something like let stir equals hello world and let stir :string equals hello world, and both of those will create a string constant called stir and have the value hello world assigned to it. But of course, one is a little more verbose. You're explicitly saying that this is a string, whereas the other one, you're essentially implying that it's a string by having hello world in quotes. So you can essentially be as verbose as you want to, which can be very helpful in some instances for readability of your code. But also, if you're not 100% sure on like a return type, for instance, you kind of get that auto keyword functionality from like C++ by not specifically stating what type it is. So kind of nice. The other thing is it's pretty trivial to expand the functionality of existing types. So this was kind of one of the principles that Swift was built on. It's kind of on this protocol idea where you can essentially add your own extensions and build upon different types. And what's really nice about that is one of the examples that I used in my Swift implementation for the encryption algorithm is currently there wasn't a string function to convert a string to base 64. But what you can do is you can write an extension that extends the string class, I guess, or string type, whatever it's called, and basically add functionality to add that conversion to or from base 64, and then you can essentially call that like you would any other function. So just like there's a dot count for Swift strings, or a dot front, get front, remove first, things like that. You can essentially call these new extensions that you write natively, which can just add to that additional functionality of types, which is super nice. The other thing I like is some of the what I'm calling C-isms, I guess, kind of similar things to C. So Swift has native support for things like pound ifs. So that's something that's really nice in C and C++. So depending on which platform you're developing for, you can essentially ensure that you're including the right includes, or maybe calling the right functions or things like that. You can do the same thing in Swift. The other thing that's nice is the ternary operators. So if you're not familiar with the ternary operator, that's essentially you have a Boolean statement and then a question mark, case, and then a colon, and then another case. So essentially, if the Boolean is true, you do the thing after the question mark. Otherwise, you do the thing after the colon. So it's pretty common for setting values. So for instance, like Boolean. So something like, if you want to increment a value, but you're not sure if you want to add one or subtract one, you could have a ternary operator that would basically be negative and then question mark -1 colon 1. And essentially what that means is if the Boolean value negative is true, you essentially return, if you will, -1, which is your negative. Otherwise, you do what's after the colon, which is just 1 or +1, and you do it that way. So ternary operators are nice. It kind of helps you not have to do if-else blocks where you just have one thing in them. So it can be nice for that. And then syntactically, it does have some similarities to C, so things like the curly braces and that kind of a thing is similar to C. And on the topic of syntax, it's also very Python-like, which is very nice, and some people call that like a modern syntax, if you will. So things like loops, for instance, aren't as verbose as they are in like C++ or Java. So if you're, writing a standard for loop in C++ or Java or even C, you have your for int I equals 0, I less than whatever I plus plus, right? So, but in Swift, it generally kind of, you don't have to do it this way, but typically the way that it likes to be done is kind of in the Python style of like for item in items, right? Like kind of that for each loop type of a thing, which you definitely can get in, C++, for instance. You can do the same thing like, for value type. So something like for const int a colon B or whatever. So like, or I guess going back to the items example, you do like for int item colon items. So you can kind of get the same functionality, but it's kind of a cleaner read in Swift. But you can also do range-based for loops as well. But it has that kind of similar syntax to Python, where rather than doing like the int I equals blah 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 I less than I plus plus, that kind of a thing, you basically just do kind of a range-based thing where it's like for I in, and then you kind of have your parentheses, and then you essentially dictate your range in there. So loops are definitely kind of more Python-like, and there are some other kind of Pythonisms where you don't necessarily need to have parentheses around your if statements. So definitely kind of a very clean syntax in that way. And the other thing that's also nice about Swift is the use of optionals. And optionals are nice because you can essentially set values as optional to help prevent runtime issues where you get a nil value, or in C++ land, that would be like a null pointer. And you can also use things like guard clauses to ensure you actually have a real value. And, with the guard clause, if you don't get a real value, you can essentially handle that accordingly, whether that's returning early, continuing through the loop, or throwing an exception or something like that. The other nice thing about it is it has kind of a package manager of sorts. If you create a file like a package.swift file, it can be super nice and convenient to manage all your dependencies for you. It can auto build code for you, and then if you define any dependencies within that package.swift file, it'll automatically pull those dependencies down and build them alongside your program to essentially ensure that you have all your dependencies. Because one thing that's nice but also kind of annoying about C and C++ is while there's a ton of libraries out there that exist for those languages, there's not really a good way to manage them. Because if you need access to like OpenSSL or libcurl or something like that, there's really no package manager for C and C++ to ensure it's installed properly or in the right place. Really, your kind of only options is either to download a local copy of the source code and like manually configure and link it into your build system, or you could install it at like the system level, and then if it's installed at the system level, you can just do it call it normally like you would with like the math library or like pthread or something like that. So in the way the Swift package manager function is kind of similar to like pip, if you will, with in Python world, or like cargo from the Rust world, where essentially you can ensure that all the dependencies will be pulled in that you might need. So definitely something that's very nice. The other thing that I also like about it is the documentation for Swift. So the published documentation that Apple has put out is pretty phenomenal. Now, it's not perfect, but it is definitely a breath of fresh air compared to documentation for other various libraries. Looking at you, OpenSSL. And it basically, any time that I needed to look up how a function worked or look up what function to use, if I had the idea of kind of what I wanted to do, I almost always was able to find exactly what I needed in the documentation, straight from Apple, and didn't have to really use any sites like Stack Overflow or anything like that. Now, I did turn to Stack Overflow a couple of times, but the vast majority of the time, if I was trying to look up how either a function worked or what function to use, I just went to the Apple's documentation directly and was able to find exactly what I was looking for. So the documentation is definitely pretty good, although I guess I should preface that with a little asterisk saying that, I am a developer. I've been coding for almost 10 years at this point. So since I kind of know what I'm looking for, it's kind of easy to comb through documentation like that because I kind of know what functionality I'm looking for. But if you don't necessarily know what functionality you're looking for, it potentially could be quite intimidating for you. But for me personally, I think it's pretty good and I found it very helpful. The other thing I want to point out that I like, and I guess this is kind of the last for the pros, and then we'll get into some of the things that I don't necessarily like, is the cross-platform compatibility with Swift. So, while it's not as prominent as other languages like Python, Java, or even C and C++, Swift can actually be run and compiled on macOS, Linux, and Windows. Now, of course, I guess I should caveat that with just because you can compile and run Swift code on Windows or Linux doesn't mean you can write like native iOS apps, for instance, on those devices, because you still need Xcode for that, and Xcode, of course, is exclusive to macOS. Now, one thing that is nice, at least in my experience anyway, is because Swift has like essentially one compiler to it, there isn't necessarily a ton of difference as far as code goes. Now, there are some kind of quirks, if you will. Like, there are some like Apple specific things that you can do in Swift that you can't necessarily do on other platforms, but it's not like, say, Windows versus Unix, programming, where if you're trying to program for native Windows using the Microsoft Visual C compiler, or like the MSVSC, blanking on the acronym, but the one that Visual Studio uses, if you write code for that and try to compile it on Unix with like GCC, for instance, you're going to be in for a bad time. Because the differences with how, the Windows libraries work versus the Unix libraries. But so far, now granted, I haven't really tested much Swift code on Windows builds but as far as like macOS and Linux goes, it's fairly one-to-one. Now, like I said, there were some instances where there was Apple-specific stuff versus not being able to do it on a non-Apple device. One of them specifically being in regards to the CryptoKit. There is a way on Apple devices that you can securely generate random bytes. But at least in my searching, I only found a way to do that with like Apple native hardware. Now, you can still generate random data on non-Apple native hardware, but I didn't necessarily find anything like specifically for ensuring like the cryptographic security. Because in case you didn't know, how computers generate random numbers is not actually random, it is pseudo-random. So essentially, if you know what seed was used, you can essentially get what random number was generated and essentially break the random number generator, which is essentially how you can do things like random number generator manipulation in old like Pokemon games, for instance. It's a hobby of some people to do that, and the reason why it's able to work is because if you know the original seed, you can essentially calculate what the random number is going to be, and you can essentially guarantee what outcome's going to be at certain points in time. But the point of cryptographically secure random number generation is essentially prevents you from being able to do that. So when you're dealing with things like encryption and using random numbers, you want to ensure that your random number generation is cryptographically secure, because if you can crack the random number used in your cryptography, you can then essentially break the cryptography. So that was one of the reasons why I kind of wanted to search for cryptographically secure stuff. But anyway, that's kind of a bit of a tangent. But yeah, Swift is cross-platform. You can write code for both macOS, Linux, and Windows. Now, granted, the install process isn't necessarily as straightforward as, say, installing something like GCC, but you can still do it. Now moving into some of the things I don't like. And starting off is function parameters. So depending on how you define your function parameters, it can be quite verbose. And essentially what I mean by this is in Swift, when you're defining a function, you can have the option to prepend an underscore with a space before the name of the variable. So you can do something like underscore data colon int, for instance, to create the data being an int. And essentially what the prepending underscore does is it basically defines, do you need to explicitly state this variable name or not? If you have the underscore, you don't need to explicitly state the variable name, but of course you need to make sure your variables are in order. But if you don't have the underscore, you have to explicitly state the name, so it can get quite verbose quite quickly if you have a lot of parameters for your function. So on the one hand, this can be fantastic for readability because you can see just looking at when you're calling the function exactly what each variable is going to. But if you have to constantly type all these names out, you're kind of being overly redundant and quite verbose depending on how your naming scheme of variables was. The other thing with function parameters is they're constant by default, or essentially a let variable by default. Now, this can be nice, but I also found it mildly annoying when I wanted to be passing a variable by value. And basically what I mean by that is passing a variable by value. When a variable comes into a function, the value essentially gets copied, so you can change it without changing the original variable value. So in Swift, it doesn't allow you to do that. And so I guess getting back to the pass by value thing, I kind of want to explain this a little bit better. So in a language like C and C++, when you pass a variable into a function, by default, it passes it in by value. So if you're calling a function and you're passing in the value str, and that contains a string, if you modify that string variable within the function itself, when you get back out of the function and return to the main loop, that variable that you passed in won't be modified at all because you passed it by value, so you essentially copied the data from that variable and into the function and didn't actually modify the original. Now, if you want to modify the original, that's where you would pass by reference, and essentially what that means is rather than copying the value into the function, you are essentially giving the address to the original value, and then that allows you to modify it. Now, the way you can ensure, now in like C and C++, you kind of get into a little of a tricky point where depending on what types of variables you're passing in, passing by value can have some rather significant performance implications, which is typically why if you're using anything that isn't a default type, to pass it by reference to basically ensure that you're able to fit that argument within the size of a register for performance reasons. Now, you can make, if you don't want that value to be changed, you can make it a constant reference to basically say that don't change this, which is essentially what Swift does by default, which is nice in some regards, and you can change it to allow it to be an input-output variable, so you can actually change it and modify it, and that change will be reflected. But if you're trying to, copy a thing, if you wanted to copy it by value, like if you're just dealing with an integer and you kind of want to use that within the function, you essentially have to make a separate copy of it at the beginning of the function in order to be able to use it like that, which personally I kind of found annoying at times. But on the one hand, the kind of nice thing about that is Swift is basically able to dynamically determine whether to just make it a let constant by value or by reference, and essentially do all that behind the scenes. Um, because kind of like I mentioned, it's technically best practice for performance reasons if you're not using a native type like an int, a double, a float, or something like that, to pass it by reference to ensure that you're only passing the address to essentially stay within the register size of the CPU for better performance. And the other thing too is, depending on how nested some of your functions can get, if you're passing like very large classes by value over and over and over again, you could potentially run out of stack space, which is not good. So essentially, passing by reference can help mitigate that. So all this to say, from a code safety perspective, it is a very smart design choice that the developers of the Swift programming language made. But at times it can potentially be a little bit annoying depending on what you want to do, always having to make a local copy of the variable. So that was just, I guess, kind of more of a nitpick thing that I had. And then we're going to get into something I labeled as a pro, which is the lack of memory control. Now, I mentioned this was a pro, but it's also kind of a con, because while I definitely enjoy the more concise nature that Swift has, not being able to control exactly how much memory I'm using is also kind of a downside, because it's just another level of abstraction from the hardware. And speaking of abstractions, Swift has quite a number of them. And while the abstractions is nice from a convenience perspective, it can also be detrimental, in my opinion, especially to new programmers or developers that are trying to understand computer architecture. And what I mean by this is, when you're working in C, you have to be the one managing your own memory, your own threads, your own sockets, and all that good stuff. But in Swift, essentially all of those things are abstracted away from you, kind of like they are in Python. But even in Python, you have to manage things like sockets and threads. But in Swift, that's kind of all abstracted away for the most part, especially the threads and the memory aspect. Because in essence, you don't get to learn why your functions run simultaneously with threads, since you don't have to worry about them. You just, call async, and, things can happen, behind the scenes. You don't necessarily have to worry about how threads work. And you aren't cognizant of how much memory your program's using. And if it's using a lot of memory, you're not necessarily sure why, because you weren't allocating any of it. Now, don't get me wrong. The fact that you don't have to worry about threads or memory management can be having to worry about those things. So like when you're dealing with C or C++, having to worry about managing threads and memory can be an absolute royal pain in the butt, and can have severe consequences if done wrong. Basically, look at at the vast majority of security vulnerabilities in the past 50 years. The majority of them are because of memory issues, and are from C and C++ because memory wasn't managed properly, or there was not a null check or a buffer overflow, or whatever the case may be. There was an issue with how the memory was managed, which quite honestly you don't have to worry about when dealing with a memory safe language like Swift. So not having to worry about that is definitely very nice, and will basically force developers to write safer code, because the language handles that all for you, and just in general makes safer code, because you can't exploit a memory error in a program if it's basically impossible to have memory errors, right? So the fact that you don't have to worry about those lower level functions is nice. But if you're actually trying to learn about, computer architecture, how computers work, how memory works, how CPUs work, how threads work, and all that kind of stuff, Swift is quite honestly not ideal for any of those use cases, because of all the levels of abstraction that it kind of puts between you, the developer, and the hardware itself. But like I mentioned, I just kind of want to reiterate this. it is kind of a breath of fresh air to have that super fast execution like C and C++ without having to worry about all that low level stuff. But again, at the same time, all those levels of abstraction can be detrimental, especially if you're trying to learn about computer hardware and computer architecture. Next up is kind of something I also labeled as a pro, which is the error handling. Now, don't get me wrong, the error handling is fantastic in Swift, but it can be quite, if you're trying to exhaustively implement every single possible catch statement or every single possible error case, it gets very verbose very quickly and super repetitive potentially also. And it kind of can be a pain. So if you're not just trying to do a generic do catch and catch every exception and just print out a generic exception, and you want to handle every type of exception differently, it gets to be pretty verbose and pretty repetitive pretty quickly, which is kind of a nuisance at times. So that is one thing to kind of keep in mind. So those were kind of the main, I guess, criticisms that I had within, working with Swift for, the course of this project and just working with it for the past couple years, working with iOS development and specifically this project. But final thoughts, I guess, is I honestly really enjoy Swift now, especially now that I understand it better. Because one thing that I've touched on with other languages is, and just kind of a general principle, is, at least for me, if I don't understand something, I tend to not like it. And this is pretty clearly seen with my experience with C. Because with Swift, when I first started dabbling with it, within iOS apps, for instance, because that's kind of what got me started with Swift. When I first started dabbling in Swift, I didn't necessarily care for it all that much. Now, granted, I didn't outright hate it like I did when I first started learning C, but it wasn't, definitely it wasn't my favorite language. But like with C, once I understood it and learned the language, I gained a much deeper appreciation for it and grew to like it. And that's basically kind of how C became my favorite language. Went from basically my least favorite to my favorite. Now, Swift doesn't have that big of a range delta, but it definitely, my perspective has definitely shifted from before I started this implementation of my encryption algorithm. It's really opened my eyes to the fact that no, Swift is not just a language for writing macOS or iOS apps, because this implementation, aside from not testing it on Windows, I did run and test it on both macOS and Linux, and it runs pretty fantastically. And of course, Linux is not a iOS or Apple platform, right? So, in my opinion, there's even examples, I think, on the Apple developer YouTube channel, I think, of essentially using Swift to write servers and whatnot. So there's definitely a lot more use cases for Swift than just strictly writing apps for Apple devices. And that's one thing that's kind of opened my eyes with this project in particular. And to be honest, now that I've gotten this solid Swift experience under my belt, I think I might look to throwing it kind of in the rotation when it comes to what language I want to write a program in. Because, before it was like, okay, do I want to write this in Python or do I want to write in C or maybe C++? Java I kind of fell out of favor with Java. But it's still something that's on the table, and I have picked it as a language in the past. Specifically, I did a vehicle cloud simulator, and I wrote that in Java, which I guess that was maybe like a year and a half ago or something like that. But still, it's something in the rotation. But I think Swift is definitely, after this experience, has added itself to the repertoire, to the rotation of potential languages that I would use for future programming projects. Because, like I said, I definitely really enjoyed using it. And yeah, it definitely grew on me, just like C did, but of course not to the extent that C, because I mean C, like I said, had a huge swing from essentially being loathed by me to being the favorite, being the top dog. Now Swift definitely hasn't ascended to that level, but it definitely leapfrogged, I would say, from not necessarily caring it for it all that much, like it's tolerable, to definitely enjoying it. So that was kind of my thoughts on Swift. Hopefully you enjoyed this, but before we end the episode, we have to get back to our trivia question for the week. So an operating system kernel runs on what protection ring on the CPU? So again, what protection ring on the CPU does the operating system kernel run in? If you said ring 0, congratulations, you got this week's trivia question correct. And if you enjoyed this episode or learned anything about the Swift programming language, definitely be sure to subscribe to the Dark Assassins podcast, leave it a rating and review, leave a comment if you're on YouTube if you haven't done so already, and be sure to share it with a friend or family member. And if you have any questions about this episode or have any comments or topics or ideas for future episodes, shoot me an email at contact@darkassassinsinc.com. The link is down in the show notes below, or if you're on YouTube, you can just leave a comment. And that's going to do it for me in this episode of the Dark Assassins podcast. Until next time, my fellow assassins, remember, bull nothing equals true. If action not equal to null, return true. I'll see you next time on the Dark Assassins podcast.